Uh, Welcome, Vasu and Abijith. I think Vasu is from Open Text and Abijith is from Ultraviolet. We are here to know more about model testing insights in CAE, how we can optimize automotive performance and safety. We're very happy to have you both with us. Over to you.
Thanks, Dipti. Thank you so much for the warm welcome. Abhijit, can you share the screen? No, it's not audible.
Not seen as of yet. I think it's coming up.
Yeah. It's fine. You can stop and reshare. Yeah, it's visible now. Yeah, just a minute. Okay. Hope I'm audible, right?
Yes, you're audible, Vasu. And
Thank
also, people who have raised your hands can lower it down. When you have a question, please put it on the chat.
Sure. I think Abhijit is also trying to speak, but I'm not able to hear him.
Abhijit, can you try talking? Yes, we're not able to hear Abhijit. I can hear Vasu.
Yeah.
Can you try without your headphones?
No, Abhijit, you're not. Not yet, Abhijit. Just a minute.
Vasu, can you try sharing your screen so that he gets to troubleshoot?
Yeah, it's fine, Abhijit. We are not able to hear you. Just a minute. Sorry for the hindrance, guys.
Yeah, no problem.
Yeah. Okay. So today we are going to myself Vasu Venkatesh and I have my colleague here Abhijit Misia. We are here to share our knowledge and experience on model testing insights about how we are using computer-aided engineering to optimize performance and safety in an automotive industry. Computer-aided engineering can be used in various industries as well, but due to time constraint, we will particularly focus on automotive industry. So the agenda for the day today, we will be having first of all we'll be having a short introduction about what is computer aided engineering, followed by the design life cycle of the process how we are following in CAE. Then we will look into some of the key techniques in CAE. Then model testing insights and correlating. We will have some practical examples on how we can perform some analysis on a real world vehicle components by simulating it, and we will also interpret the results to see how we can better optimize them. And then we will see some of the real world examples that has happened in our history. We have plenty. Followed by that, some features and benefits in CAE. Now, introduction to CAE. CAE is also known as computer aided engineering, which is used to test the vehicle components or any components by simulating using software without any physical prototypes, just by building the model using um, the CAD, the initial CAD which we have based on the client requirements. Let's say there is a design department, based on their analysis existing failures of any components or some insights from their client requirements, they'll be providing us the CAD, which is the initial phase design. Using CAE, we will be simulating that design into our simulating tool, which is CAE, and we'll be performing analysis. If you see the right hand side diagram, the flow chart, which is particularly break down what is specifically happening in CAE. Like we'll be based on the design, we'll be performing discretization. Let's say an example of handlebar assembly. In a handlebar assembly, there are various components like handlebar, spacers, risers, bolts, and nuts to fix them all together. So all these components together, we can have an handlebar in a motorbike. Now, each component has multiple degrees of freedom, and we have to analyze those degrees of freedom to understand how it behaves in a real world under different forces, or how we are, different motions and suspensions. Now, we have to perform discretization for these each and every component to make that infinite degrees of freedom to finite degrees of freedom for faster calculations. And in real world, we have this bolts and nuts to assemble them together. But if you want to simulate exactly into the software, we have to perform assembly. CAE tool will also helps us with those advantages as well, to ensure that we are having a calculation in such a way that it is more accurate to the hand calculations. And we'll be providing boundary conditions based on the materials we have used, and based on the other factors, let's say load, other parameters. And the CAE tool will help us to compute them based on the inputs we have provided. And once the output is generated, as a CAE engineer, we will be analyzing them to understand whether it is ready for the physical prototype, or we need to change the design in the CAE stage itself while in the process of simulation. If it is ready in the physical prototype, and if it is working fine in the physical prototype as well in the testing, then it is ready for the final production. We will be releasing it to the production. But if anything is failed in the physical prototype, on physical components failed, then there will be some modifications with respect to the design itself. So we'll be requesting them with the CAD team. So this is the overall life cycle of CAE, the process, how the testing happens in CAE. Now, let's talk about some of the key techniques in CAE. Like there are various methods in techniques, like using this simulations, like performing testing in the automotive industry. There are various techniques. Let's say there is an analytical testing, analytical method, where for smaller components we can perform hand calculations, and the accuracy will be more here when we are performing hand calculations. In that cases, we can perform using analytical method. But for larger components, we need other methods. Like we can use numerical method. Under numerical method, there are various techniques like finite element analysis, computational fluid dynamics, multi-body dynamics, thermal dynamics, noise, vibration, and hardness calculation analysis. So there are various techniques involved here. In finite element analysis, we will be using this to analyze the structural integrity of the vehicle and durability of the each component. And there are various analysis we can perform, like stress analysis, crash analysis, durability analysis, fatigue analysis, etc. We will be seeing all these things in some time. Now, computational fluid dynamics, like let's say fluid, as it says, we can consider fluid as either a gas or a liquid. Now, this fluid flow in an vehicle, to analyze this fluid flow, we can use computational fluid dynamics. If I'm saying that we can use this technique, means there are like different formulas to calculate the different parameters, which I'll explain you in detail in upcoming slides. Now, as a fluid, we can also say some examples, which I can say now: air cooler, refrigerator, and a petrol tank, fuel tanks, etc. And multi-body dynamics, one example which I can quote is a suspension, calculating the suspension, analyzing the suspension system of a vehicle, and motions, like when a vehicle is in a motion, when a vehicle is traveling, and at different speeds, and if it is changing its directions, the steering wheel, how they are using the steering wheel to control the vehicle from moving from one direction to another direction. So those kind of comfort mechanical systems, to analyze those things, we can use multi-body dynamics. Now, I want to explain in detail about, either Abhijit will be explaining you in detail about how we can use the finite element analysis technique to model the some of the examples which we'll be seeing, and how he is going to correlate the results to optimize the design. Abhijit, over to you.
Okay, some technical issues there. So I'm presenting via Vasu's screen. I'm audible now?
Yes, you are.
Okay. Right now we can check how we are optimizing the performance of a vehicle component using FEA finite element analysis techniques with the help of a CAE tools. In market, there are various CAE tools such as Hypermesh, OptiStrux, Abacus, ANSYS, etc. We have used Alter Hyperworks to model this component. This is a simple car wiper. This is a single car wiper. Here you can see. Also, can you play the video? This car wiper has multiple components, as you can see here. It has some cladding brackets and guiding brackets, and wiper is also there, arm and holding bracket is also there. You can see this one is the blue one is the guiding brackets, and this yellow is the wiper and arm and holding brackets are there. These are multiple components. Will come will, this assembly is this entire this each individual component will form an assembly. For calculating the performance of this component, we have to discretize into finite, because each and every component has infinite degrees of freedom. We have to discretize into finite degrees of freedom. You can ask a question, why we have to make them into infinite to finite, and why we are going to perform those structural analysis. Right now, if we are designing a new design, means it should have some design parameters, and it should have some criterias. Based upon this criteria, it will operate. Right, in the similar way, in optimizing its performance of a component, natural frequency is the basic design criteria which we will calculate before while designing a new design. Next slide, Vasu. Okay, this is the first stage. That's I said that there are three stages in three stages in FA technique. This is the first stage, which is known as the pre-processing stage. You can see this is not the CAD. This is the exact model of the CAD, which we have discretized into a finite degrees of freedom. You see, each and every parts are we have discretized. And the next stage is we have to assemble the each and every component into a single assembly. These car wipers are assembled with bolts and screws in real life, but how we are going to perform in simulations, that we have to know. Here we have just we have just connected with the 1D beams and some rigids we have used. The red zones you can see is those are those screws and bolts which we have assembled based upon the CE simulations. This red zones will replicate those contact, and these an individual component will form an assembly. After creating those things, we have to assign those materials. Why we have to assign? Without assigning, it won't calculate those calculations. That we will check in the upcoming slides. Right now, in right hand side, you can see I have assigned aluminum material for this arm, and for after assigning, we have to some material properties to those materials. That is the Young's modulus. E is the Young's modulus of the aluminum material, and nu is the Poisson's ratio, and rho, which is the density of those aluminum material, which will define the mass. Mass means weight of the component. Next slide. And this is the second stage of our CE technique. which is the solving stage. Here, to find out the natural frequency in CAE, we are using certain methods. There are EAGRL land cost method and ASMES, which is automated multi-level subtracting eigenvalue solution methods. We have used EAGRL land cost method, and this M of A plus K of U is equal to 0, which is the general governing equations, where the solver will solve based upon these equations. We have assigned those material properties, the I said now the density, which will be defined from this formula. And in right hand side you can see Fn is equal to 1 by 2 pi root of k by m, which is a natural frequency formula for the natural frequency. With this formula we can do hand calculations for a simple structure, but viper take a viper, it's a complex structure while calculating its performance, so we can't calculate with those simple formula, hence we are using those formula. As I said, in left hand side, we are using EAGRL method. From here, I'm going to remind one concept. There is one concept, each and every component. Basically, while you are designing any component, let's say, as Vasu said, handlebar is wiper and helmets, airbags, every components will have n number of natural frequencies. For checking our purpose, we have just extracted only the first 10 natural frequency of the component. After setting up these setups, the software will simulate and we will get the results in post processing, which is the final stage of the CA techniques. These processing we will view in the hyperview, and tool is there. As I requested for first 10 natural frequency of the component, you can see it in the left hand side. With these frequencies, as a CA engineer should have to know which will be the critical frequency and which will be the critical modes and which will affect the real life performance. As a CA engineer has to know. Go to the next slide. That is the first mode, and this is the second mode. Based upon these modes frequencies, you can see in the image of the top of the right top corner, you can see the mode shapes are varying. That's the frequency is also varying. With those shapes, it will the mode shapes of the component will also vary. We have to know which will be the critical one. To understand this concept more, I will go with the real life example, which is the famous Tacoma Bridge collapse, which occurs in 1940 on USA. You can clearly see in this video. They have designed this bridge for some certain limitation, keeping certain natural frequency, keeping up to the limit. But in after opening, it has excited more because of the wind interaction. You can see in this video clearly, it is flexing more. Why? Because it's flexing. It has it has some natural frequencies. After wind interaction of the wind, it gets some excited. So we are getting two frequencies there, naturals and excitation frequency. Because of those frequencies, we are getting resonance. Resonance is nothing but when the natural frequency meets up with the excitation frequency, we will get some higher amplitude, that is known as the resonance. If the resonance occurs, means definitely it will fail in component failure. You can clearly see in the videos. At the particular point, what will happen? The resonance occurring. After that, finally, the bridge will collapse. This is the exact situations it is happening in the real life. And that's how we have to check those natural frequency. As I said earlier, natural frequency is the basic design criteria while we are designing one component. You can see here, it's breaking, right? And we can't alter those excitation frequency because it's not in our hand. It will depends based upon the load acting on it, but we can optimize the natural frequencies because the natural frequency is based on our design and what material we are going to choose, so we can alter natural frequencies. Hence we have to check those things, and these are the reasons for the failures. Why? What are these are the reasons for the failures of those bridges, such as I said already, it's a wind interactions that causes the excitation frequency and torsional vibrations. This is the twisting mode, which is really the critical mode for the bridge. Vasu, can you go to the third previous slide? They can understand more. Before one, before you can see in the third slide, mode 3, it's a twisting, right? This will be the critical one for the wiper, and that's how we, and the frequency is also almost 16 hertz only. So we have to optimize better to increase this frequency. Yeah, I can go to the next slide. and that's how we are optimizing the performance of this vehicle component. Next, we can look into how we are optimizing the safety by having a look into the simple example helmet. This is one example. This example I have modeled and dropped the helmet from a 1 meter height to check the stress concentration region. Just assume if an investor is going to invest some money in producing some helmet, means he has to invest in materials and he have to invest some money in the labor charge, etc. The thing he have to invest, right? After investing, after at the final production, if he is getting a poor quality of helmet, means what the use of investing? So we can't change. Many things are lost, right? Money, time, everything as a resource, everything has lost. So if we are using the CAE simulations, we can alter the material by changing those material property as I defined earlier. As I said in Viper, like that we can change in this process also. Here I have assumed PA6 material for the outer covering and dropped it from the 1 meter height, and I check the stress concentration regions. In the third image, you can see at the fillet region, it shows some red zone. If I'm not satisfied with those values, I can change easily the materials by changing those densities, Young's models, Poisson's, or whatever the things I said earlier. Like this. Like this, we can optimize this performance of an each and every single vehicle component, and we can improve the strength of a component like this. Next.
Hello. Yeah.
Yeah, audible.
So let me walk you through few of the features and uh, benefits of CAE. Yeah. So using CAE tools.
Also, you're not.
Hello.
Sorry, guys, there is some trouble with Abijith's laptop. So imagine a world where AI handles repetitive simulation tasks for you. CAE tools powered by AI are already making that reality by optimizing the designs faster than ever and reducing manual errors. This is the revolutionizing approach for product development, allowing engineers not only to focus on innovation rather than a regular process. It's also allowing users to come up with a new analysis perspective using AI and cloud platforms. Now, think about the power of collaboration. With cloud platforms, engineers can work together in real time, whether they are in the same room or in a different continents. And the best part, accessing to the virtually unlimited computational powers increases the analysis time and faster simulation, seamless teamwork, and better outcomes as well. Now, previously, we have used separate tools for analyzing different techniques like structural analysis, crash analysis, thermal, fluid analysis, etc. But imagine all the type of techniques are available in one tool will make it gives us a 360-degree view for a product's performance, making simulations not only faster but also far more accurate. And now, coming to the benefits, there are various analysis we have got. It's a really proven way that we have improved all these things, and the references are already there in the next slide. Let me walk you through few of those achievements we have made. Now, when we talk about the safety, crash simulations come to mind. CAE tools have improved simulations accuracy by massive 90%. This directly impacts the bottom line of 50 to 20% reduction in post-production changes. That in that way, we have reduced cost, increased like we have saved time, increased we have properly utilized the resource efforts as well. It's not just about the cost savings, but also saving lives as well. Now, here's a tangible example. Let's take an airbag. Using CAE, we have achieved 10 to 15% increase in the deployment speed and accuracy. This means airbags are now more reliable in critical moments, which makes a huge difference in safety ratings and consumer trust. Now, errors in design can be expensive. We all know that. But what if we could detect and fix them at the earlier stage when they happen, before they happen in the physical stage? CAE tools are doing just that, reducing human errors to 60%. The shift not only improves the efficiency but also ensures we are delivering high quality design to production. Finally, let's talk about the impact on manufacturing. There are a lot of human errors are happening while manufacturing a physical prototype. First time, the quality has improved by 15 to 20% thanks to CAE. Less rework, fewer defects, and smoother to production in this agile, fast-paced world. So that's all about complete there is a very depth topic, but I just wanted to give a very high level of how using the CAE tools, how we are simulating or mimicking a physical prototype, and how effectively we are calculating these results and analyzing various possible uncertainty situations which are nearly impossible to test in the real world as well. So if there are any questions, we are good to take. Hope no more questions. Okay. Thanks everyone. Thanks for listening actively. If you have any questions, you can reach me out on LinkedIn. You can visit Agile Testing Alliance page to find my ID over there. Thanks everyone.
Thank you.